Perfect. Okay, assalamu alaikum everyone. My name is Rasoul and this is Rawad Turko. We're doing today practice questions for physio-pulmo. So the way we like to do it is we like to have it interactive. So we got the hardest questions we found for everything through books, anything we found, and then we're trying to go over them. So we have around 2 to 3 questions per lecture. We sent you guys the form and we kind of looked over the feedback and decided to include more questions for some lectures and include less for others. And inshallah, we'll try to go over this with the help of you guys. So I'm expecting everyone to answer questions here, and then we're going to explain why the questions are right, what the answer is right, what the other answers are wrong. So this will let us start. We're going to start with lecture 1, intro. Physiological dead space calculated by Bohr equation is. What do you guys think?
E. Ooh, who else says E? Okay. E.
Yeah, can you keep open? Can you have the chat on the side or something?
Can you move the chat to the side? I don't know if you
have it. Just leave it.
Okay.
E. Okay. Anyone else? Okay, this should be a straightforward question. The answer is E. So it's a straightforward question. It's basically recall, but we need to reiterate this point here. So when we talk about physiological dead space or anatomical dead space, so the physiological dead space is basically the anatomical dead space, which is basically the trachea bronchi plus whatever is not getting ventilated. So you're always going to have your anatomical dead space, which is the trachea and the bronchi. But sometimes in some patients where there's where they have some obstruction of some alveoli, then you get that physiological dead space that is increased. So it'll be the trachea bronchi plus whatever is not getting perfused or ventilated. That's why it could be either equal or greater than the anatomical dead space.
Right. So guys, let's say this right here is the anatomical dead space. Okay, obviously there's no gas exchange happening in your trachea or your main bronchi, right? Stuff like that. There's no gas exchange happening, but there is gas exchange happening here. Okay, so this is your anatomical dead space and this is your respiratory zone, right? Your alveoli. Now let's say you cut off you cut off ventilation to this alveoli, and this alveoli. There's no longer any gas exchange happening here either. So now your physiological dead space would be the same anatomical dead space that you have here, plus whatever alveoli are blocked. So this then becomes alveolar dead space. And this gets added to the physiological dead space. So your physiological dead space would then be your normal anatomical dead space plus your alveolar dead space. Okay, does that make sense?
That's why in normal patients, it can be equal. And then in patients that have some obstruction, it will be greater.
Right.
Okay.
Right. But it's always physiological dead space is always at least just anatomical dead space. Mm-hmm. So it's always equal to or greater than. Does that make sense? Cool. I'm gonna take that as a
perfect. Okay.
Perfect. Thank you guys.
Okay, so this is for first lecture.
Little
warming up. Yeah. Question 2. What volume remains in the lungs after a normal expiration?
Okay, so we have a few different answers. Okay, wow, very wide range. Okay. Can somebody who said, let's start with B. Somebody said B, right? I think it was. Yeah, Malak. I think Malak. Guys, by the way,
yes.
Please don't feel the pressure to answer if I call on your name. If you don't want to answer, just be like, I'm good. But we'd like this to be interactive, and there's we're chill. Yeah, there's no need to be nervous about it. So yeah, Malak, why do you think it's B?
Actually, I didn't calculate it, but I think it's E. I changed my answer.
Okay. Okay,
Bold. I
then
like it.
when would it be B, do you think?
Because after normal expiration, we will have residual volume, and we will have end like the maximal expiration volume. So both is functional residual capacity.
Okay. Okay, sure. Now somebody who said C, expiratory reserve volume. Can somebody tell me why you think it's C?
Okay. So expiratory reserve volume, C, that would be the right answer if they said after a maximal expiration. Okay. Since they're doing a normal expiration, expiratory reserve volume is not the answer.
It's not.
I was answering the question.
So
Okay.
so the answer is E.
The answer is E.
So why are the other options wrong? So first of all, tidal volume. Tidal volume is wrong because
Okay. Tidal volume is wrong because that's not your. They said, okay, first of all, let's break the question down. They said what volume remains in the lungs after a normal expiration. Okay, so normal expiration, this would be a normal inhalation up here, and this would be a normal expiration. So after a normal expiration, you're down here. Okay, so Mukshib and all the other people who said C, your expiratory reserve volume would be part of the volume that's left in your lungs after a normal expiration. But it wouldn't be the total volume left in your lungs because you always have that residual volume. So your functional residual capacity is your residual volume plus your expiratory reserve volume. So you're not completely wrong. It's still there, your expiratory reserve volume after a normal expiration, but it's not your it's not your total volume. Okay, so the total volume that's remaining in your lungs after a normal expiration is your functional residual capacity. Now, Rasoul and I, we looked through this lecture. We found that every single thing taught can be summed up using this picture. So we made a little lung volumes cheat sheet for you guys. Okay. Actually, you know what? First of all, before we get into that, so the question is which volume remains in the lungs after a normal expiration? Can somebody tell me when you would have your, let's see, your residual volume, D, when would you have your residual volume be the only?
After maximum expiration.
After maximum expiration. So that's how you want to think of these, that's how you want to solve these questions when you see them on your exam. Okay, try to think like, okay, this volume I'd get when I see a maximum expiration, this one when I see maximum inspiration, stuff like that. So that's why we made this cheat sheet for you guys. So the volume in your lungs left after a maximum expiration, thank you to whoever answered it, right, is your residual volume right here. Okay, after maximal expiration. Oh, this is sick. Okay. Volume in your lungs after a normal expiration, we just answered this, you're down here. So everything left would be the functional residual capacity, right? Maximum volume inhaled after a maximal expiration. That means you're down here after a maximal expiration. So you go all the way down here, this is your maximal expiration, and then you inhale as much air as you can, and you go all the way up here. What is this equal to? Without, what is this equal to? Sorry?
It's the vital capacity.
Yes, it is the vital capacity. Perfect. Okay. Maximum volume inhaled after a normal inhalation. So this time you're right here after a normal inhalation. So you're up here because when they say normal exhalation, you're down here. Normal inhalation, you're down here. So that's everything from here to here. What is this?
Inspiratory reservoir.
Perfect. So that's when you go like, so I just took a normal inhale and then I go like all the way in. That's your inspiratory reserve volume. Okay. Normal volume inhaled after a normal expiration. Now this time you're down here instead of up here. What would this be? From here to here. We're almost done, guys. It's just Three more.
Respiratory capacity.
Yes.
Yeah.
Yeah. Respiratory capacity.
Yeah.
Make maximum inhale after normal expiration. Okay. Yeah. Perfect. Oh, sorry about that. Okay. And let's just do one more, just for fun. Volume in your lungs after maximum inhalation. So this is all the volume in your lungs after you take a deep, deep inhale.
Total lung capacity.
Perfect. Total lung capacity. That's everything. Okay. So make sure, guys, before you go into the exam, that you memorize this extremely well. Okay. The questions are super easy, but you don't want to, like, they're like haram to mess those questions up on the exam. They're really, really easy marks. Okay. Just make sure you memorize this. Okay.
We're gonna move on.
Move on to question 2, lung volumes.
Volumes.
Okay. So this one needs a little bit of calculation. So prepare your calculators and all that. And I want at least one person to help me solve this. Okay. A healthy patient is connected to a 1.5 liter bag containing 9% helium and rapidly rebreathes over 10 seconds until the helium concentration in the bag and lungs is the same. If the final helium concentration is 3% and the subject is at functional residual capacity, when he is connected to the bag, what is his FRC? Now, first of all, can somebody tell me why we're doing this, what we're trying to see, before we get into the calculation stuff? What are we doing here? What's the point of the helium?
We will calculate the residual volume.
Residual volume.
Residual volume, perfect. Why? Because you cannot measure the residual volume. Since it can never be exhaled, it can never be expired, we can never measure it. So the way we measure the residual volume, and in this case also the functional residual capacity, because it includes residual volume, is by doing this thing that's called helium dilution method. Okay, so that being said, let's answer this. I'll give you guys a minute. Is somebody willing to answer this, by the way? Okay, with a B. Okay. Abdul Hassan, can you tell me why you think it's B?
I think because I convert the percentage of helium to 0.9 and I minus 0.9 minus 0.3 and divide it by the liter. 1.5 divided.
Okay. See, I think you have the right formula in mind, but you might have interchanged a few values for one another. But I think you have the right volume in mind. But it's not. Does anybody have a different answer?
I think the problem is that he calculated the residual volume, but he didn't add the ERV, right?
Okay. The thing about this question is they don't tell you how much the residual volume is. So C. Okay, perfect. Yes. So the answer is C. So guys, questions like these, they might seem really hard because we're so done with math. We don't want to do any math anymore from high school. I get that, but it's actually when you look into it a little bit, it's very, very basic chemistry. Okay. So the answer is C. Now, do you guys remember that whole thing, C1V1 equals C2V2 from high school chemistry, the dilution thing? You guys remember that? Was it just me?
Yes.
Okay, cool. C1V1 equals C2V2. So I'm gonna just explain the chemistry behind it just a little bit because I don't want you guys to memorize the formula. I want you to truly understand why we're using this formula to get the functional residual capacity. So C obviously is concentration, so the concentration of the gas. So in this case, C would be 9% helium. And in this case, when we're talking about this person, this healthy patient, 9%, that's your concentration. That's equal to what? 0.09, right? 9% equals to 0.09. V is equal to your volume, actually, obviously. So this is 1.5. Oh, my writing is not that great. 1.5. Okay. Concentration times volume gives you C times V. gives you your number of moles, or obviously the amount of gas present, right? Do you guys remember that from chemistry? N
CV.
N is equals CV, or C equals N over V. We're getting into the chemistry a little bit. Like, you don't need to know this stuff.
Yes.
I want you to understand it properly. Okay, so that means CV, C1 V1. Okay, before you do anything, C1 V1, that's equal to the amount of gas, or amount of gas particles in a specific compartment. Okay, so let's say we have these two compartments and they're blocked. So they're connected by this little pipe right here, but for now they're blocked. Okay, so we have a specific concentration. Let's say this is 0.09, and this is 1.5 liters. Okay, we have the specific concentration of gas particles, which is 9% or 0.09, and the specific volume. So that's C1 V1. C1 V1 equals 0.09 times 1.5, and that's the amount of gas here. When you open this compartment, when you open this blockage, basically now the gas that was here will be dispersed equally among this compartment and this compartment. Okay, does that make sense? So the concentration, because these gas particles are spread over a larger volume, the concentration will what? Decrease or increase? You're spreading it over a larger volume.
Decreases.
Decreases. The concentration decreases because you're spreading it over a larger volume. And then what would happen to the volume? Obviously, increase. But we still have the same amount of gas here in this figure as in this figure. We have the same amount of gas. That's why we derive the formula C1 V1 equals C2 V2. Basically, we're saying the gas that was here and just here is equal now to the gas that's all over these two compartments. It's the same amount of gas. But now you have these two different concentrations in these two different volumes. And from these values, you could now get any one of these four values. So if you know C1, V1, and V2, you could now get C2 by knowing just those three with this formula. In this case, what are we trying to get? We're trying to get V2. Okay, so what we do, if I can go backwards, yeah.
It's always good also when you already know this and you're going over the question, it's good to write, for example, this right here, he put Rawad put 1.5. Okay, this is V1.
Yes.
Right? This right here, C1. Now we can be like, okay, what are we missing here? And how can we rearrange the equation to get what we're missing?
And this, C2. Okay, so now we have 1.5 times 0.09 equals to 0.03 times x being V2. Okay, I'm going to do just a little bit. I'm going to try to get it. 1.5 times 0.09 divided by 0.03. Okay, 4.5. I got V2 as 4.5. Can somebody tell me why I don't see 4.5 here in the options? V2, like we got V2. V2 is 4.5. Right? That's supposed to be it. Right? Why is that not it yet? We have to subtract 1.5. Perfect. I'm so glad somebody's with me. Yes. So we said this is 1.5. We're trying to get this and only this. This is your functional residual capacity. We're trying to get only this. Okay. V2, because I said we're spreading over a larger volume. V2 is 1.5 plus whatever volume you have in your FRC. Because you're spreading it over a larger volume. Obviously, now the helium gas is both in this 1.5 liter bag and in your lungs, in your functional residual capacity. So to get just the functional residual capacity, you do that number, 4.5 minus 1.5, to get 3 liters. Okay? Does that make sense to everybody who didn't get it right the first time? Abdul Mohsen, does that make sense?
Yes.
Okay.
I just have a problem with this question.
Yes.
Thinking about, like, I think that we are getting the residual volume from this equation because we exhale maximally, at the max. So only what's left in the lungs is the residual volume.
See, that is true in your slides. In your slides, I think they use the example saying that you take now, like after you take a few, like you breathe in a few times the equilibrium to reach equilibrium with the gas between this bag and your lungs. Afterwards, I think they say that you take a deep, deep exhale. And then so that all that's left is your residual volume. Here, they don't say that. Here, they say that the subject is at FRC. So whatever they say, just take that as the truth. So if they say your patient is at residual volume, then you're at residual volume. If they're at functional residual capacity, then they're at functional residual capacity. Can't we just do volume times C1 minus C2 over C2? Yes, you can. You can, but again, I was just trying to explain the whole. You can derive this formula as much as you guys want. Okay, you can play around with this formula, like rearrange everything, you do whatever you want. I'm just trying to get you guys to understand the concept instead of memorize it. Okay. So as to answer your question, in your slides, it's written as residual volume. Now you're using this method to measure specifically your residual volume, okay, or your functional residual capacity, because and only because your functional residual capacity includes your residual volume. So the end goal is to reach your residual volume. Okay, could you repeat why you subtracted 1.5? No worries. Okay, so let me erase everything first from these two. Okay. Now, we have two cases. The first case, we're looking at the gas just in this little tiny compartment. Okay, and this little tiny compartment would be the bag, the 1.5 liter bag that they told you about. Okay. All right, so I'm gonna also erase all this. So the 1.5 liter bag, that's what's here. That's where you have your helium as of now. This is before you open it up to the lungs. Okay, now you have your 1.5 liter bag. We're trying to get this volume right here, and only this volume. This is your FRC. This is obviously before you open it up to the lungs. Okay, so here you have a specific concentration of gas that they told you is 9%, and you have the volume obviously is 1.5. Once you open it up to the lungs, the gas that was originally just in here, will be in both here and here. But the key concept is it will disperse equally among those two compartments, your lungs, or specifically your FRC, because that's what they said you have, and this 1.5 liter bag, the same 1.5 liter bag. Okay, so this becomes, both of these together become V2. This was V1 here, just the 1.5 liter bag. Both of these compartments together become V2 because the gas is in both compartments. That's why it's V2. So, but you're trying to get this and not this. So in the end, when you find V2, you subtract this volume from it to get just the FRC instead of both of them together. Does that make sense? Okay, perfect.
Yes, thank you.
Perfect. So one last time, the inert gas diluting method. Helium gas is added to the spirometer and its concentration is measured prior to opening the valve, prior to opening this valve right here. The amount in moles of gas, obviously I added moles just to get you guys to understand the concept, is equal to the concentration C1 multiplied by the volume C2, or V1, sorry. After opening the valve, the gas disperses equally among the lung and the spirometer, both of them, giving a larger volume, V2, made up of the lung volume, FRC, plus the spirometer volume alone, which is V1. So the V2 becomes FRC plus V1. The concentration also increases, or sorry, this should say decreases. Sorry about that. The concentration also decreases as it is dependent on the volume. The amount, however, stays the same. So C1 times V1 equals C2 V2. This is used to calculate the unknown lung volume. That's whatever it is, whether it's RV or FRC.
And they should tell you in the question.
And they would be telling you. And
yeah,
even if they don't tell you, but like the choices are all going to be numbers. So they're not going to say the RV is this, the FRC is this. Right? So just select whatever number that you get based on this calculation. Okay. Okay. Perfect. Let's move on. Now, P18 and P19 lung mechanics. Okay, the diagram above or below right, shows three different compliance curves, S, T, and U, for the isolated lung subjected to various transpulmonary pressures. Which of the following best describes the relative compliances of the three curves? Okay. Wow, wait, is this all just right now? I looked away for 1 second. Inshallah.
That's right now.
Yes, okay, perfect. E. Good.
Okay,
This
just
is
move
very,
on.
very, very straightforward. I think you guys understand this. Do you guys need me to explain this any further? I'm just gonna read it through really quick. So compliance is defined as the change in volume divided by the change in transmural pressure difference. If a small change in the systemic pressure, PTM, causes a large change in volume, so like in this case, you have a small change, like from here to here, and at the same time, a very large change in volume, the lung is obviously more compliant. Thus, the slope of the line increases as compliance increases. So the steeper lines are going to have higher compliances. This one is going to have the lowest compliance. Okay.
Okay, let's like when we have high volume, when we get low compliance or high compliance?
Low.
For high volume? Okay. When we're talking about pressure. We're talking about pressure.
Question?
When we're talking about when pressure increases, does compliance increase or decrease?
Decrease.
Okay.
Okay, so make sure you guys always know the relationship between different
Those two
here.
parameters.
Yeah.
Okay. So like you have to know what happens, for example, when you have increase in volume, or when you have decrease in volume, or if you increase in pressure and decrease in pressure. This all depends on your lung volumes too. Okay, so depending on which lung volume you're at, will determine what your compliance is like. So, for example, at FRC, when you're at FRC, which is again at the bottom of your exhalation, the bottom of your tidal volume, that's where your lungs are at their most compliance. Once you start to get to either extreme, either residual volume or TLC, that's when it's going to become a bit harder to, or the lungs will become a bit more stiffer and will become more elastic. The word is, they'll resist this change in volume. Does that make sense? Okay. I think we move on. This was wrong. Yes. Okay. Two alveoli of different sizes, 1 and 2, obviously, are connected by a common airway. If the surface tension is the same in both alveoli, the pressure produced by the surface tension will be higher in which alveolus, and in which direction will the air flow between the two alveoli? Okay, wonderful. Okay, cool. Before we show, obviously the answer is A. Can somebody tell me what equation we're looking at? What's the name of this equation? The name of this formula that we're using?
Pressure is equal to 2 times surface tension divided by radius.
Yes, that's the one. Or in other words, the Laplace law equation. Yes, that's the one. Perfect. So the answer is A. We're looking at the Laplace law, which is basically the pressure, as you said, is equal to 2 times the surface tension over the radius. Okay. Since this is inversely proportional to the pressure, the radius. Oh, what's going on? Since this is in the denominator, that means when radius increases, pressure would what?
Decreases.
Decrease, because they're inversely proportional. As this increases, this will decrease, and the opposite is true. When this decreases, the pressure increases. Now,
okay, when diameter increases, what happens to the pressure?
Yes, that's a good question. Diameter.
Decrease.
Yeah, so it's the same thing.
It's the same thing.
Same thing, yeah. So like sometimes I remember those questions, like when there was radius involved, they would give you, instead of the radius, they give you the diameter. And you need to understand that diameter is like, I mean, you guys already know this, but you guys haven't thought about it since high school. So like, it's probably like, it's in the back of your head somewhere. But diameter is basically radius.
Like in our case, yeah, it's 2 times the radius.
2 times the radius.
For our case, that's the same thing.
Yeah.
Okay.
So it's important to know that that's the same thing.
Yeah. So in this case, going back to the question, they said the alveolar pressure is higher than P1. Which one of these is the higher, or sorry, is smaller? Which one of these alveoli is smaller? Is obviously number one, right? That means one has a smaller radius. And as we said, smaller radius, increased pressure. So then the pressure gradient law will tell us obviously that the pressure is going to go from the higher pressured one, from 1 to 2. So the direction of airflow will go from 1 to 2, and the alveolar pressure obviously is higher than in alveolus 1. Perfect. I think everybody's okay with this. And finally, for the last question, in lung mechanics, we put 3 questions just because it was 2 lectures, even though I know that this shouldn't be that hard for you guys, but it was 2 lectures, so we put 3 questions in. A 27-year-old pregnant woman is rushed to the emergency department following a car accident and delivers a premature baby by cesarean section or C-section at 30 weeks of gestation. The baby is 3 pounds 4 ounces. The newborn is tachypneic and dyspneic. Which of the following changes to the alveolar surface tension and lung compliance are expected in this newborn compared to a healthy newborn? Wow, mashallah. Yes. Okay. Perfect. Yes. The answer is B. Do you guys know what disease this infant has? You can just give me the acronym. It's okay.
Respiratory distress syndrome.
Yes. Yes. Infant respiratory distress syndrome, or IRDS, or RDS. Yeah, it's the same thing. Or surfactant deficiency, as you said. D. Yes. Surfactant deficiency. So surfactants. Yes.
This disease wasn't in the slides, right?
It was.
It was written.
Yeah, it was written. It wasn't in the
Wasn't in the slide. It was written in the transcriptions that the doctor has on the PowerPoints.
Yeah, Dr. Shams has these notes section in his slides. So if you were to open them, it says that.
I think it's like two lines or something. He just brings it up.
I think so. Can anybody confirm? Right, this wasn't in the actual.
That's what I remember.
That's what I remember too.
Yes, it was there, but it was there in parenthesis notes section.
Yeah. Okay. Perfect. But make sure that you guys know this super well. It's very easy, very easy. But it is like, I don't want to get too ahead of myself, but it might be like among the most quizzed topics, concepts in all of Pulmo, or specifically, surfactant deficiency, or specifically this lecture. It's very high. So make sure you know this very well. So surfactants would. Surfactants reduce surface tension by decreasing density of water molecules at air/water interface. Okay, so obviously your lungs, if you were to take a look at your lungs, obviously there's alveoli there and everything and all that, but it's mostly made up of air. Okay, and your pleural fluid, that's the thing that's right after your lungs, it's water or it's fluid, right? So you need something to decrease the tension between those two things. Those are 2 different interfaces, water and air. Okay, if you were to, if they were to just meet and touch without anything to reduce that tension, it would be very hard to expand your lungs or to make it compliant. That's why you have surfactants. Surfactants are these tiny little molecules, and there's obviously a specific mechanism of them. You don't have to know them. You don't have to know that, for example, the physiology of a surfactant. You just have to know that when it's there, it will decrease the surface tension between the air and water molecules, and it will increase compliance. So when it's not there, the surface tension would increase and your lung compliance would decrease. Okay? Okay, that's it we just knocked out 3 lectures. We just knocked out 4 lectures, sorry. Intro, lung volumes, lung mechanics 1, lung mechanics 2. Now the next one, airway resistance.
Airway resistance, yeah. I tried to find, I went over the lecture and I tried to find a little overpass and practice questions. There isn't a lot of stuff that they would quiz you on from this lecture, and I tried to find like the most high yield thing they would quiz you on. So so this is where this question comes in.
This question came in midterm.
It did?
This exact one?
Yeah, Poisson's law.
Oh,
midterm?
Yeah, because they did this in cardio. Also, the same formula is repeated twice in cardio and in pulmo, right, guys?
Oh, okay.
Yes.
Yeah.
I see. No, for us this was in pulmo, so we only got it in the final. But I remember solving this question when I had CVP and I didn't know how to solve it. So, mashallah, you guys obviously
They're set.
yeah, you guys are set. The most important, yeah, the answer is E. And this is where I was telling you guys about the radius and the diameter. In our exam, they gave us the diameter. They gave us the diameter and they told us what happens to it. And then here you have to like solve for the radius. And then, for example, here, what would the diameter be if the radius is 81?
We double that.
We double the answer. So I think if I remember correctly, they gave us the options like this. They gave us like R, and it was like half R, and then 2R, so stuff like that. So you guys need to understand how to solve it if they give you diameter, and you need to like notice if they give you the diameter or the radius. But what's important here is this equation here in this lecture. So can anyone tell me what this equation is? What are we trying to find here?
The resistance of the airway?
Yeah, so there's the resistance of the airway. So how much resistance is how much resistance we have when we're trying to breathe in. So what's PA here?
Alveolar pressure.
Yeah, alveolar pressure. So what makes it easier for you to understand or to memorize this equation is we know resistance is pressure over volume, or not volume, airflow here. So when we're talking about pressure, we're talking about the pressure of how our alveolar is getting ventilated. So that is due to two things. That is due to alveolar pressure, obviously, and it's due to the airway opening. So where we're getting the air. So like when you understand that it has to do with how the air gets from your mouth, from outside to your alveolus, then you understand that you have to subtract alveolus minus airway opening over airflow, which is right here. But I bet you guys already memorized it from CVP. So do you guys know what N here is? I'm just trying to make sure you guys understand this before we move on. You guys know what N stands for? Viscosity, yes. So this N is viscosity. L here would be
Length.
Yeah, so longer volume. And then you guys know what pi is, and then R4 is the radius. You know? And that is the most important equation in that lecture. I found that there's nothing else that they were asking about in terms of calculation in this lecture.
Right.
And I think is also an important part to remember. I couldn't find any question that would test this topic here, but here did you guys understand here what the difference between the resistance, what happens in resistance here? You guys understand it?
Yes.
Okay, so in at the bottom where we have our terminal bronchioles, we have a lot of like small alveolus. So when we have small alveolus, we have a lot of surface area. Because we have so much surface area, we have a lot of volume that is in there in the terminal bronchioles. That means when there's a huge amount of volume, we don't have a lot of resistance. The resistance is very, very low over here. The resistance is high only in certain generations, they said, and that is in the first 4 generations. It's in first 4 generations because we will have decrease in the volume. They are very big. The first example, trachea and the bronchi in the beginning, they're very big. That means they will have a lot of resistance. That means only in the first 4 generations we'll have an increase in compliance. After the 4th generation, we'll get a constant decrease in the compliance because of the increase in the volume in those bronchioles. And then here, do you guys remember what's the disease that could happen in terminal bronchioles? There's also disease, just like RDS. They have it in like doctor has it in like one sentence. Do you guys know what it is? It's called the silent lung disease. And it's silent because
Yes. He
it's a
mentioned.
tumor. Sorry?
Yes, the doctor mentions about this that the tumor in lower airways won't be detected as if it will have like if it's something like that.
Exactly. So again, because we said there's a lot of volume that happens in the terminal bronchioles. That means we don't have a lot of resistance. That means when there's a tumor that's compressing on those bronchioles, because there's not a lot of resistance, very, very low resistance, we won't be able, like that tumor will not close enough alveoli to cause a reaction, to cause symptoms for this patient, because there's not a lot of resistance. That's why this person could be living with a silent disease, silent tumor, and not feel anything, because it's not affecting any of the alveoli, because there's a lot of volume and not a lot of resistance. So, for example, if that tumor were to happen above in the first 4 generations, because there's a lot of resistance, you could tell when there's something compressing. So that's why it's silent down there, and that is also very important to understand, because they could bring you a question about it in the exam too.
I want to just really quickly explain how you get 81. Obviously, we know the formula, okay, but you're not going to put in some big values and then try to calculate for it. You don't really have a good you have the exam soft calculator, but it's not good enough. So you have this formula, obviously 8 times viscosity. I don't know what to call this symbol. I'll just call it N. 8NL over pi R4. What's the only one of these you care about? The only one you care about?
Radius, I mean.
Radius. So what I like to do is I like to do this. Let's say what I like to do is I like to take every single other value as 1. Everything is 1. So 1, which is your resistance. Let's start now. 1 equals 111 times 111. Okay, that's what I like to do. 1 over 1. 1 over 1, 4. Because your radius, obviously we only care about your radius. So ignore everything else. Ignore every single other thing. 1 over, because this is all 1, over 1 to the power of 4.
Except for the 8. Yeah.
Except for the 8. But the 8, again, because we don't care about anything else, I'm going to take everything as 1. I'm just going to ignore every single other thing. Because at the end of the day, these are constants. Everything else, when related to our thing, we don't care about anything else, so we're going to take them as constants. Meaning that whatever change that you do to your radius, that change exactly will be proportional in your resistance and nothing else. So 1 over 1 to the power of 4 equals 1. Now we reduce our radius to 1/3. Okay, so now we have 1 over 1/3 to the power of 4. Okay, so if we do a little bit of quick math, we get 1 over 3 times 3 times 3 times 3 is going to be 81. And then 1 over that, obviously, 81. Right? Does that make sense to everybody? 1 over 3 to the power of 4 is equal to 1 over 81. Right? 3 times 3, 9, times 3, 27, times 3, 81. Okay, and 1 over that is 81. Does that make sense? So you can ignore everything else. We care about the radius. We'll only look at the radius. Radius to the power of 4, obviously, because that's the most important part, is the 2 to the power of 4 part. Okay, so if they say, for example,
Diameter.
Yeah, if they say diameter,
Yeah.
if they say the diameter, then what you do is you take, let's say they took the diameter to 1/3. So what you do is you take D over 2 over 3.
Yeah.
Right? And then you solve for that. But it's the exact same thing. If they were to say radius, doubling the radius, then you do 1 over 2 to the power of 4, and then you solve for that, right? And then you ignore every single other thing except for the radius, because it's the only thing you care about anyways. Does that make sense? Okay, next lecture, assessing pulmonary functions. The maximum expiratory flow volume curves shown in the next diagram were obtained from a healthy individual, that's the beige curve, and a 57-year-old man who complains of shortness of breath, that's the blue curve. Which of the following disorders is most likely present? Okay. Perfect. Perfect. Go back. Does it not say? Oh, I must have. Okay.
Yeah.
So yeah, the answer is B. Okay, weird thing that just happened here. Hold on. Okay, cool. So we're gonna do 2 questions in one, basically, because I think I must have put the I must have forgot to put in the explanation for this one, but that's okay, no worries. So emphysema. What does emphysema do to your total lung capacity? Let's ask that question. It's obstructive. Yes, it is obstructive. And the only obstructive
It makes exhaling harder.
It does make exhaling harder, but what does it do to your TLC? I think they were saying it. Yes, it increases your TLC. So off the jump, this is your normal individual. This is where you start normal. This is after they took a deep breath in and then exhaled all the way out. So this person, this healthy person's total lung capacity is right here. Mine is right here, or ours is right here. So it's increased. Immediately, that should tell you that it's an obstructive disease, because restrictive would be down. We'll talk about restrictive in a second. But obstructive immediately would increase your total lung capacity. So if you see a curve that starts, further up than your normal healthy individual, 99.9% of the time it's going to be an obstructive disease. And what else does it do to your residual volume? It makes exhaling harder. That is true. So what happens to your residual volume if you have trouble exhaling? It will increase your residual volume too. So when this person goes all the way up here, this person can only exhale to up to here. So it's doing 2 things at the same time. It's increasing your TLC, so it shifts this curve this way, and it increases your residual volume. So this diseased person, can only exhale up to here. Down to here. Okay, so that's why this would be emphysema. But another way to solve it, just if you didn't know anything and you got this exact question, this is how you would solve it. Asbestos, I didn't take it. Kyphosis, I didn't take it. Scoliosis, didn't take it. Silicosis, didn't take it. Tuberculosis, didn't take it. I only took emphysema. So there's 2 ways to solve this, but use the first method.
What would happen to? Did you talk about FEV over VC?
That's the next one. That's the next question.
Okay.
Yeah. I think they're doing that. Hold on. Yeah.
Okay, let's bring. What would happen in emphysema? What would happen to FEV over FVC?
The ratio.
What happened to the ratio?
Do you guys remember that whole thing? FEV forced. Okay, the ratio. Yes,
okay.
Good.
Okay. There's a question. What does the
slope down curve represent? Okay, so this is your rate. This curve down represents the rate at which you're exhaling air. So the rate at which you're exhaling air right here is very fast, right? That's basically what it's telling you. And then it sort of slows down when you're exhaling. This is the rate at which you're exhaling the air. Okay, not the volume specifically. Volume is determined right here, but the curving up and the curving down, it's your airflow per minute, right? Your liters per minute. So you're exhaling this much per minute. If it's a slope upwards, it means you're exhaling very fast. So if it's a slope downwards, it means you're exhaling sort of slowly. That's okay. You don't really need to dissect the graph too much. This graph is only really truly, it's only very important to understand the emphysema and the fibrosis, obviously. So just if you know this much just from this graph, that's pretty perfect. It's fine. Yeah, no worries.
What would happen if the graph was something like this?
Fibrosis.
Fibrosis.
Perfect.
Fibrosis or what? Or yeah, restrictive.
Restrictive, yes.
So again, do you guys know? Do you have a question on restrictive disease and after or no? This one is it restrictive? Okay. What's restrictive disease? What happens to the? Okay, perfect. You're already gonna go.
Yeah.
Okay. Let's do the second question. We'll go over
the second question. Yeah. Okay. So this is obviously it's fibrosis. But again, fibrosis obviously does the opposite of whatever emphysema does. Emphysema makes it harder to exhale. Fibrosis makes it easier to exhale, harder to inhale. If it's harder to inhale, then you can't inhale all the way upwards, which means your TLC is going to stay decreased, right? Your residual volume is going to also decrease a little bit because I said it's easier to exhale. So whatever residual volume you have normally, it would be a little bit less than that in a fibrotic or in a restrictive disease. Okay, so this is simple enough. So this emphysema, this fibrosis, and that's the only thing they're ever going to ask about this graph. Okay, so it's either, and again, same thing. It's not this. We didn't take this. Okay, we did take this, but it's not this. It's not this, not this, and not this. Right? They're only ever going to ask in terms of fibrosis or emphysema, or they might say just obstructive disease, restrictive disease. Okay, but that's all the examples that you need to know. Okay, question. Okay, and obviously, yeah, here's the explanation slide. You guys can just look this over later. We already talked about all this. Okay, question 2 from assessing pulmonary functions. The following diagram shows forced expirations from a person with healthy lungs, which is curve X. This is a healthy. Should have probably changed the colors. That's fine. And from a patient, curve Z. So this person is normal. This is our patient. Which of the following can best explain the results from the patient? Somebody says B. Okay. B. 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 Can somebody tell me? Okay. So the answer is B. True. I'm gonna put like 2 questions into one basically. Can somebody calculate for me what FEV1 is for the normal patient? The normal patient's FEV1. So this is 1 second right here, from here to here. We're going from 5 to 1. Perfect. Okay, Malik already got it. Yeah, perfect. So in the first second, you're going all the way up from 5 to 1, and then this is over. Obviously 5 liters. So you're exhaling 4 out of 5. That's 80%. 80%, and then your patient's FEV1 is obviously from here to here 3 over 5, or sorry, 2 over 5, 40%. Specifically 40%. It's not really 5. Yeah, 40%. Okay, so this is your little cheat sheet again. Yeah. So this is 2. 2 over 5. 2 over 5 is 40%. Right? Yeah. Oh, I'm sorry. No, I'm sorry. You're going back up. Oh, okay. I just made a really, really big mistake. I'm really glad you guys caught that. Yeah. I'm not going to sit here and try to act like I did that on purpose. Definitely didn't do that on purpose. But yeah, actually, it's not 5 liters. It's 4 liters because you're going up from 5 to 1. So this is 4 liters, and you're exhaling in 1 second 2 liters, right? So it's 2 out of 4 actually. So it would be 50%. You're right. Okay, because you're not going all the way down to here, like in the normal patient, you're going down to here. Okay, what does this immediately tell you? The fact that you're going down to here, not all the way down to 0. Immediately, what does that tell you? That your residual volume,
obstruction?
that it's an obstruction. Perfect. Because you're going, you can't exhale all the way out. You're having trouble exhaling, which means immediately it's an obstructive disease. That's why you get emphysema immediately. So I added a little bit of a cheat sheet for you guys.
There's a question. Can you explain how?
Explain how.
There's a question.
Oh, I thought he was asking. Yeah. Can you explain what exactly did you want me to explain? We got the values. Okay, sure, no worries. Okay, so right here, you're starting from this point. This is at the top of your inhalation. Basically, what this test wants to do is you're checking how much a person can forcefully exhale in 1 second compared to the rest of their forced vital capacity. So there's two values. There's FEV1, which is your forced expiratory volume in 1 second. 1 stands for 1 second. So everything you can forcefully exhale in 1 second, that's your FEV1. And then there's your FVC, which is your forced vital capacity. That's how long it takes for you to exhale everything all the way down to your residual volume. Okay, so we're measuring 2 things. Now, usually in normal patients, healthy patients, you should be exhaling in 1 second 80% of your force, of your vital capacity. In 1 second, if I were to take a deep, deep breath in and exhale all the way out very forcefully, in 1 second, I should be down to 80%. I should have exhaled 80% of my vital capacity. That's for normal patients. Now, people with obstructive diseases, they have a harder time, obviously, exhaling. So in 1 second, where a normal person would exhale 80% of their vital capacity, a person with an obstructive disease would only, for example, exhale 40 or 50%. And that's because they have a harder time exhaling. So we're getting these values from this diagram exactly. So you're starting at 5. Okay, this basically, so the y-axis is your liters, your volume. So you're starting from 5 here on the y-axis, and your x-axis is the seconds, how long it takes for you to exhale this volume out. Okay, so in a normal patient, which is x, you're going from here, from 5 in 1 second. So from here to here in 1 second. So we're talking about from 1 second to 2 seconds. From here to here, you're exhaling 4 liters, right? From 5 to 1. 5, 1, 2, 3, 4. You're exhaling 4 liters out of 5. Okay, because then after this 1 second, you're going all the way down. You're exhaling 4 out of 5, which is 80% in 1 second. So your FEV1 for the normal patient is 80% because you're exhaling 4 liters out of the 5 that you have in your vital capacity. In the diseased patient, or the person with the obstructive disease, in the same second, instead of going all the way down to 1, they're going from 5 to 3. But notice how their curve doesn't go all the way down to 0, like in the normal persons. It only goes all the way down to 1. Okay, that tells you out of the forced vital capacity, the total forced vital capacity is less than the normal person's forced vital capacity. So this time it wouldn't be 3 out of 5. Or sorry, I keep putting 3. It's 2. It wouldn't be 2 out of 5. It would be 2 out of 4 because they're only going all the way down to 1 and not 0. So 5 minus 1 obviously is 4. So this person's FEV1 is 50%. The diseased patient. Does that make sense? Okay, perfect. So again, this is your tiny little cheat sheet, right? So in a normal patient, again, the FEV1 over FVC ratio is 80%. A person with an obstructive disease, the FEV1 FVC ratio is less than 80%. Okay, and the restrictive FEV1 FVC ratio remains 80% or increases slightly. Okay, but always if it's less than 80, immediately it's obstructive. And if it remains 80% or increases slightly, it's a restricted disease. But the main thing about your restricted disease is that the curve kind of looks weird and the FEV is increased. Okay? That's the main thing about
I have a question.
Sure.
Can you go up to the question?
Of course.
Like for emphysema, isn't it supposed to be that the graph shifts to the left?
Okay. I'm glad you made this mistake. You're talking about this graph.
Yeah.
You're talking about this graph. These are 2 different graphs. Okay, so this graph is measuring your flow rate, and this one is measuring like the speed. I guess it's sort of similar, but they're 2 different graphs. Okay, so it would shift it to the left when you're talking about this graph. But when you're talking about this graph, it's something else.
Okay.
Okay. Yeah.
Okay, moving on to alveolar ventilation. Experiment is conducted in 2 persons, subject T and V, with identical VT, which is 1,000 mils. Dead space is 200. Ventilation frequency is 20 breaths. Subject T doubles his VT and reduces his ventilation frequency by 50%. Subject V doubles his frequency and reduces his VT by 50%. What's the total ventilation and what's the VA for the subjects? So this is a calculation problem. So they're asking for 2 things. They're asking for total ventilation, which is this right here, and they're asking for VA, which is this right here. So what would happen? Okay, we're getting E's.
Does
Okay.
anybody have any other answer other than E? Because you don't know, it might not be E. You never know.
Okay, it
Maybe
is E. So we're looking at total ventilation and we're talking about VA. Okay, first thing, let's dissect this question really. What's VT here? What does VT stand for?
Tidal volume.
Yeah, so this is tidal volume. Yeah, which is 1,000 mLs. And then we're talking about that we have dead space, 200 mLs, and we have frequency, which is 20. Okay. Now, they're asking us for total ventilation. What's the equation for total ventilation? Yeah, it's done. Perfect. Okay, VT times frequency, which is pretty straightforward here. So VT is 1,000, and then frequency is 20. Okay, that's for T. We have for T, we have ventilation is okay. Since for T we have double the VT, so here we have 2,000 times. Reduces his ventilation by 50%. So instead of 20, we have 10 now. What do we have here? We have 20,000. Okay. For subject V, subject V, what happened to?
Very weird to put T and V when they're talking about
V and
VT.
T, I know, yeah.
It's weird.
Subject V has double the ventilation frequency, so 40. And then what happened to the VT is decreased by half. So here we're talking about 500, which equals to what?
20,000.
20,000 as well. So far we have this right here, which is the total ventilation. Total ventilation, what is it? Is it VT? It's like this, right? I think.
That's how.
I don't know.
Total ventilation. Is it
Total
T,
ventilation.
V? It's weird.
Yeah.
The whole T is the V's.
It's the total volume. It's the volume, let's say. So the volume here we have is equal. So we're talking about those three.
Okay, so you could exclude.
We can exclude everything else so far. Yeah. We know for sure that they're equal. Okay, now when we're talking about VA, what's the equation for VA? Or alveolar ventilation? Do you know what the equation for VA is?
VD minus VT minus VD multiply respiratory frequency.
Perfect. Okay. Okay, so for T, we have VA is VT. So what happened to their doubled their VT? So 2,000 minus 200.
Because their dead space volume remains the same. This is your
That's
anatomical dead space, by the way, we're talking about. You're not gonna double your tidal volume, but then also somehow double your dead space volume. It's gonna stay the same.
What is it? So 2,000 minus 200.
1,800 times 10. 18,000.
Okay, 18,000. I did not need the calculator for that. For V is what? We have 500 minus 200 times 20 times 40, right? Because they're doubled.
I was wondering what
frequency doubled, yeah. So 300 times 40 is 12,000. Okay, so here we have T is higher than V, and that's why E is the answer. If I got this question in the exam, I would be, I don't know, I would be.
Tidal volume affects alveolar ventilation more than frequency, right? I mean, it's very sure you could say so, at least in this case you could say so, but that's only because we're doubling this and the and we're halving the other thing. Like we're dividing, we're dividing their tidal volume. The subject V we're dividing their tidal volume by 50%, while the other one T we're doubling it by 2000. So that's the only reason that there's such a major difference. Okay, if we were to say the same, if we were to have 1000, obviously higher frequency for subject T, then obviously you'd get the higher alveolar ventilation, and this would be just off of the frequency. Okay, so both of them affect your alveolar ventilation, but it just depends on what values the questioner is giving you.
I think it does. I think you're right when you say this because we also look at dead space always.
Yeah.
So wherever our ventilation tidal volume is, it's going to decrease because of our dead space. We have to subtract it by the dead space. So that's when it would also change the answer because it's not just the tidal volume, it's not tidal volume minus the dead space volume.
Yeah.
Is this question okay? Do you have any questions about this? We don't? Okay. Before we move forward, we already have this equation right here. In this lecture, we also talked about partial pressure of the alveolar pressure of oxygen. How do we find alveolar pressure of oxygen? So this guy right here, how do you find it?
Inspired oxygen minus PaCO2 over R.
Okay. Perfect. Okay, and how do we find PaCO2?
I think we will flip the equation.
Okay, so this is where it's different. So for PaO2, it makes sense because I'm gonna write it first so I can explain it. Okay, when we're talking about alveolar partial pressure of oxygen, we're talking about the oxygen that we get in the alveolar. Okay, so that is gonna be what's that gonna be? That's gonna be the inspired oxygen. So the oxygen that we inspire, which is, by the way, it's around 20%, I think.
21%.
21%. Yeah.
21% in the atmosphere.
Yeah, we get 21% of oxygen when we inspire, minus the difference between basically the difference between oxygen and carbon dioxide when it's in the alveolus, which is this equation right here. So that's how we find PaO2, which would make sense and it's pretty easy to understand. Yeah, for PaCO2 it's different. PaCO2 we're talking about as we got in the chat here, it's gonna flow PaCO2, the flow over the flow in the alveolar times 863, which is the atmospheric.
I think it's a constant, right?
The constant, yeah. So it's the CO2. So the ventilation of CO2. The airflow, the flow of CO2 over the flow of the alveolar, flow in the alveolar, which is both CO2 and O2. So that's where when we divide VCO2 over VA, the difference here, that fraction would give us the flow of oxygen. Then we multiply by the constant to get we multiply it to get the flow of carbon dioxide, and then we multiply it with the constant to get the pressure of CO2. Okay, so it's really, really important to get both, to understand both equations, and to memorize both equations, because they will give you questions that purely for you need the equation to understand it, to get it right. Okay. I think I have, yeah. I really put here everything, like all the equations that I think are important in this lecture. I think you guys will have to memorize these. But again, like when you go over every single one of them, you'll understand what. So for example, we already know. But when we try, for example, those two, when we went over them, and you guys really try to make sense of why it's like this, then it's easy to remember that you guys understand that we need to read the ventilation to get read the airflow to get the pressure. So try to make sense of why of the equations so you can understand it better, and then you memorize it better.
By the way, was this lecture was this the same lecture that they did the inspired PiO2 equation in?
Yeah.
Okay, I think let's add this one too, I think. So then you have, I'm gonna add a fifth equation, which is inspired oxygen pressure. Okay, so that's equal to 0.21, or the fraction. So we'll just put fraction here, but it depends on where you are. So person at sea level, 21%. Person in high altitude, less than 21%. Person receiving what's it called? Supplemental oxygen, usually 100%. Okay, so that's where the difference is. So the fraction, whatever it is, most of the time it's going to be 21%. I think times barometric pressure minus pressure of H2O. I think does that sound right to everybody? Is that right?
Yeah, that's right.
Right. Okay, and that's because when you're inhaling, you're going to be inhaling, all the gases that are in the air. Okay, whether it's nitrogen, oxygen, carbon dioxide, you're going to be inhaling all of it. Okay, plus with some air, with some water vapor. So you want to subtract the barometric pressure from, you want to subtract the water pressure from the barometric pressure, multiply it by the frequency of, or not frequency, the fraction of oxygen in the air. So 21% of all the gaseous molecules in the air are oxygen molecules. So that's why we get the pressure. That's why we have this fraction right here, which is 21% times the barometric minus the water. Okay, that's the fifth formula. And we move on.
Okay, we can move on now. So let's move on. Arterial PO2 and arterial PCO2 from 5 patients in the ICU are shown. Which of the following is hyperventilating? Which patient? Yeah, we will send the PDF when we're done. We have a different version. We're gonna send to you guys.
Yeah.
Inshallah. Yeah. So
Patient 5.
Okay. Patient 5. Okay. Does anyone? So patient 5 is right. That is correct. Why is the patient 5?
Because hypoventilation means low oxygen and high CO2.
Yes.
Perfect. That's
Pretty much.
exactly, yeah.
That's exactly
it. Yeah. So when we have hyperventilation, what happens to the alveolar ventilation? Does it decrease? Does it increase?
Decrease.
Yeah. So hyperventilation means increased alveolar ventilation.
Decreased.
You
said increased.
Just hyperventilation means decreased alveolar ventilation. Since we have a decrease in alveolar ventilation, so first of all, what we need to think about when this person is hyperventilating, in the lecture too, I think the doctor was emphasizing on the fact that what happens to carbon dioxide is what happens first. So when this person is hyperventilating, we have high PCO2. What's the cutoff? When we know this is PCO2, this is PCO2, PCO2 is high. What's the cutoff? What's the number?
The normal number, where if you go higher than this number, that's where you have hypoventilation.
Or hypercapnia.
Yeah, hypercapnia.
Do we know? 40. Yeah.
40.
So more than 40 means hypercapnia, means there is high PCO2. That's when we say there's hypoventilation, when there's high PCO2. And then when there's high PCO2, we're hypoventilating. Why? So we can increase, then PO2 would increase, so we can get the compensation to go back to normal, to metabolism. So when there's high PCO2, that's when we get hyperventilation, and then that would then result in an increase in PO2. Okay. Which of the following answers would be when the person's hyperventilating?
No.
What'd you say?
2. It's not 2. Actually, I don't think that
it's a multiple answers. Okay,
it's none of those actually. Yeah.
Yeah, it's what would happen in hyperventilation? Sorry, ignore my question. What would happen in hyperventilation? What would happen first in hyperventilation?
It's not, guys. It's none of these choices.
Yeah. That's
We didn't read the
ignore my
choices
question.
before we answered that question. Yeah,
No.
there's none of those is right.
What would happen in hyperventilation? Yeah, first of all, what would happen low CO2, and then we get okay, perfect.
So it's none of these, obviously, because
it has to be less.
Yeah. So as Rasoul mentioned, guys, the first thing that happens with hypo or hyperventilation, when they put the word ventilation in there, look at the CO2 first. Okay, because sometimes they'll ask you a question where you'll have normal PCO2 and increased, for example, O2. That is not hyperventilation. It's very, very important that you make the distinction. Ventilation, when you do hyper or hypoventilation, the first thing and the main thing, like realistically, the main thing that you should be looking for is the levels of carbon dioxide and not oxygen. Okay, because why isn't so correct answer for the second question? I'll answer that in a second. Hold on. So, 2, you are correct. Your PCO2 is decreasing, which is good. That's the first thing that should happen. But your PO2 is also decreasing. But in hyperventilation, what should be happening is this increasing and this decreasing. So actually, patient 6, if we put a right answer for hyperventilation, this would be like 110, and this would be like 30. This would be hyperventilation, or 115, for example. Because this should be increased. The normal oxygen levels are obviously 100 millimeters mercury, or 98, like something like that. Hyperventilation would be increased oxygen levels, decreased PCO2. But the first thing you should be looking for is PCO2, because sometimes they'll get you this increase or this decrease without any change in PCO2. That wouldn't be hyperventilation or hypoventilation.
So this answer would be correct. This answer would be correct because basically in their lecture, the doctor is only talking about CO2. So there's a decrease less than 40 in CO2, then we get hyperventilation is what the doctor has. So if we ignore this right here, and this is the question they give you, which of the following is hyperventilation, then it would be B.
It would be. Yeah. It would be D or 2.
D, because the cutoff is 40. So remember the cutoff is 40, and remember to always look at PCO2 when we're talking about hypo or hyperventilation. Okay.
And then secondly, look at the O2.
Yeah.
Okay. This is the next one, Mine. Yeah. Okay. If an area of the lung, this is, by the way, we're up to pulmonary gas exchange. I think we're more than halfway done, right? Yeah. Okay, perfect. We're doing well. If an area of the lung is not ventilated because of bronchial obstruction, okay, bronchial obstruction, just to make it clearer. Okay, right here. Bronchial obstruction. This is your alveoli, by the way, just in case you guys didn't catch that. The pulmonary capillary blood serving that area will have a PO2 that is, so you have, actually, I feel like this is not that great. Okay, so we have an E. Okay, hold on, let me just draw this a bit better. Okay, and then we have this capillary. So this is alveoli, and this is a capillary. Okay, here you have 40, because this is 40 millimeters mercury, because that's how much your mixed venous blood average is. That's how much the oxygen pressure is in your mixed venous blood normally. This is at the beginning of the capillary. Here, if there is no problem in the diffusion, and there's no problem in the, if there's no blockade here, this will be equal to whatever the alveolar pressure is. This at the end of the capillary, it will be equal. So if there's normal perfusion and normal diffusion of the gas, this will be close to 100 millimeters mercury. But if there's a blockade, then what would happen? You said E. Could you tell me why you think it's E? So if
Yes,
you guys,
because mixed venous is the one like the arteriole coming, the blood in the arteriole coming before going to the bronchiole or the alveoli, as going from the, like, as passing, the PO2 will decrease.
okay, not exactly. Not exactly. It wouldn't decrease. So first of all, let's talk about what would happen normally, and then what would happen in this case. So normally you're inhaling oxygen. Okay, you have your PiO2 and your PCO2 and all those things, and this right here would be 100. Right? Can we agree on that? That your alveolar pressure normally, in normal circumstances, normally it would be close to 100 millimeters of mercury. Yes. Okay. Yeah. So Maya got the. Okay. So 100 millimeters mercury in your alveolus. That's normal. Okay. So in a normal situation, this would go from 40 all the way up to 100 millimeters mercury, because the whole point of your perfusion, the whole point of perfusing the capillaries, or sorry, the lungs with blood, is to reach equilibrium between the pressure, the oxygen pressure in your blood, in your capillaries, and the oxygen pressure in your alveoli. Okay, so you're trying to get more oxygen from the alveoli. That's why it will increase in normal situations from 40 to 100 millimeters of mercury. Now, if the area of the lung is not ventilated because of bronchial obstruction, meaning there's no air that's coming down here and reaching the alveoli, you have no oxygen that's coming down and reaching its alveoli. So this alveolar pressure, it doesn't make sense for it to be 100. Okay, because there's no air going there. There's a bronchial obstruction. So instead of diffusing from here to here, from the capillary and exchanging the oxygen for the carbon dioxide, instead of doing all that, it will just continue through the capillary with no gaseous exchange. When that happens, it will stay at 40, so it will be equal to the mixed venous pressure. Okay, it wouldn't be lower than the mixed venous pressure because you're not losing more oxygen. You're just either you're increasing your PO2 in normal situations when there's normal diffusion, or you're remaining the exact same when there's a blockade or where there's a bronchial obstruction. Okay, does that make sense? So this is it. So this is the explanation. So O2 uptake is usually perfusion limited. That means when something is perfusion limited, that means in normal conditions, the only thing that would cause more oxygen to be in the blood is more perfusion, because there's no diffusion limitation, meaning that the oxygen has no problem diffusing from the alveolus to the capillary. Okay, so there's always, and the thing about perfusion limitations is that there's always the line of PO2 is always touching the alveolar PiO2. So this is PO2, okay, and this is your capillary PO2. At the beginning of the capillary, this is the length of the capillary, by the way. So if we add the same diagram, right here, it's going to be 40, as they said here, and at the end of it, it's going to be close to 100 because there's that diffusion happening. This is normally. Equilibrium is reached between alveolar and arterial PO2, and the only way to increase O2 in the blood is to increase perfusion, so to have more blood flow within this region. Okay, now in the case of bronchial obstruction, which is what we have, the lung will not be ventilated. So this alveolar PO2 will not even be 100. The arterial PO2 will not be able to equilibrate with the alveolar PO2. Thus, it will remain equal to PO2 of mixed venous blood. It will remain down here because alveolar PO2 is not 100. You're not able to get that perfusion, you're not able to get that perfusion going, to get that diffusion, going. So instead of being able to go all the way up here and equilibrate with the alveolar PO2, it will just stay down here. So it will stay equal to the mixed venous blood. Does that make sense? Okay. All right. Second question from pulmonary gas exchange. Which person would be expected to have the largest AA gradient? Which means basically the biggest difference between the alveolar and the arterial pressures of oxygen. Okay. Perfect. Okay, great. So the answer is A. Does anybody have a different answer? Is anybody confused about why this is A before I get to explaining it? Okay, so I'm just gonna explain it very quickly then. So a person with pulmonary fibrosis, somebody who answered A, can somebody tell me what trouble you would face when you have pulmonary fibrosis? Why would you have that gradient, that big difference between the alveolar and the arterial pressures? What's the main thing that's compromised when you have pulmonary fibrosis? Yes, you would have trouble inhaling, but specifically for like when we're in the context of the AA gradient, when we're talking about why this air from in the alveolus is not able to diffuse properly to the capillary. The main thing is your diffusion capacity, right? Your diffusion capacity, and specifically that whole thing, exactly. You increase the diffusion distance, and you're increasing the what's it called, the width, or what was it, the thickness? I think one of the values or one of the factors in that formula was the thickness of it. You're increasing the thickness. When you're increasing the thickness, you're decreasing the diffusion capacity because you're not allowing more oxygen to diffuse from the alveolus to the capillary. So that's the main thing that's compromised. Now, let's talk about why. One thing that I like to do, and this is what you should do with pretty much every single question you solve, is do the elimination method too. After you get the right answer, or even before you get the right answer, tell yourself, oh, it can't be B because of this. It can't be B. Why? Because a person who is hypoventilating due to a morphine overdose, if they're hypoventilating, okay, they would have decreased arterial PO2, but they would also have decreased alveolar PO2 because they're hypoventilating, right? So the gradient, so the difference between this and this would not be great. It would not be a great difference because it will be able to equilibrate. Like you will have arterial pressure that is equal to the alveolar pressure, but the only problem is your alveolar pressure is already low. That's why. So lower PaO2 and hypoxemia. So the lower PaO2 is the main thing because they're both low. Not, it's not that one is high and one is low. They're both low. So there's no gradient. Person at 12,000 feet above sea level, this is basically the same as saying hypoventilating. Lower PaO2 because you're at a higher altitude. Okay, so there's not enough oxygen in there, and hypoxemia. It's basically the same thing. Person with normal lungs breathing 50% O2. Okay, 50% is obviously a lot more than 20% or the 21% that you have in the atmosphere. So this will be higher alveolar PO2, and thus it will be higher arterial PO2. They'll both be equal, and they're normal lungs. So the fact that they specify that they're normal lungs means that you'll have no problem in the diffusion process. And the same thing with E. Okay, so it can only be A. Okay. Wonderful. That's it for pulmonary gas exchange. Does anybody have any questions about either one of these questions? It's either this one or this one. Both.
Or anything, really.
Or anything. We can go back to. We can do cardio if you guys want to. No, we can't.
That's good.
Perfect.
Okay. Okay, our next question is the fallen PVR or resistance due to exercise is because of what? So what decreases pulmonary vascular resistance? Okay, perfect. So, okay, it is D. Don't worry about this. It is D. Might have moved when we saved it, but why? First of all, what do we mean when we talk about distension of pulmonary capillaries?
Increasing blood flow in capillaries.
Sorry?
Increasing blood flow.
Sure. Yeah. That is true. Yes, but when we're talking about distension itself, what does that mean? Is what's happening to the capillary? The capillary is right here. When we talk about distension, what's happening? Yeah, increasing diameter, so it's getting bigger. It's getting bigger. That means when something's getting bigger, that means the resistance in there is decreasing. So this is a pretty straightforward answer as to why. Why is decrease in arterial and venous pressure? Why does that cause an increase in resistance? Okay, so when we have decrease in either pulmonary artery or vein pressure, we'll have a decrease in the capillary pressure in total. So that means we have decrease in the pressure. When we have decrease in the pressure, again, we're having decrease, there's less flow, blood flow or air flow happening. That means the resistance is still pretty high, or it's still pretty, like it's still constricted. Okay, and then what's hypoxia? What happens with hypoxia? Let's break that down.
Low oxygen
Low oxygen.
in the
Sorry?
low oxygen in the tissue.
Yes, and then how would that affect the resistance?
Resistance would increase.
Resistance will increase due to what? So when we have hypoxia, that means we're not getting enough oxygen. What's happened to the carbon dioxide here? So when we have hypoxia, there's not enough ventilation that is causing an increase in carbon dioxide. So that would cause hypercapnia. When you have hypercapnia, that means the tissue is not getting enough oxygen. That means all the alveoli will constrict, so we can have more blood flow going into that area. So we need more oxygen in that area, so that area will constrict, so we can kind of cause more blood flow to go in that area. Okay, so this is why. So here, this one increases resistance, and then increase in alveolar pressure. Increase in arterial pressure or venous pressure would also increase resistance here. Okay. All right. Now this goes kind of hand in hand in this question too. This is a question I made because I feel like we need to get that straight. What's the answer here? High ventilation that results in bronchial constriction causes what?
Okay. Can somebody tell me why it's A? It's fine, guys. There's no there's no wrong answers. Or there are wrong answers.
This also goes into what we already talked about. So first thing that the Dr. Shams was talking about, when we're talking about high ventilation, what does that mean? This means that we're hyperventilating. And what did we say happens to us when we're hyperventilating? What's the cause of, first of all? What happens? We look at what? Here we look at the carbon dioxide, right? Yeah. So we said in the question we got up there, when there's hypoventilation, we are getting an increase in PCO2. Is that right? So when we're hyperventilating, that means we have low. That means we have low CO2.
I think
So we have low CO2. That means we are dealing with hypocapnia here to begin with. And since we're dealing with hypocapnia, we are also we'd be dealing with hyperoxia. Here I put, so the answer here would be, it's not C actually. Again, it's D, as you guys said. And this is to explain what happened. So here again, we're getting hyperventilation. when we're getting hyperventilation, that means we are getting a lot more airflow happening due to the hypocapnia that we already have. So there's low CO2. When we have low CO2, we are trying to increase the CO2 that we are exhaling. And how does that happen? By when we try hyperventilation. And then when that is happening, we get hypocapnia, we get hyperoxia. And then that would ultimately cause bronchoconstriction.
Okay. So let's I think this question is we got it, I think, from
I got it.
Yeah, we got it from like one of the unrelated textbooks. We kind of thought it might be a bit challenging. It might be a worded a bit weird. So let's just stick to the concept for now. So what's the main thing that's happening here? The first thing that's happening is I'm just gonna erase all this, is the hyperventilation. Okay, the hyperventilation. So you have one alveolus with high ventilation. Immediately, what's gonna happen to this specific region? Hyperoxia. Okay, a lot of oxygen because you're ventilating a lot, and you're also at the same time losing a lot of oxygen. Obviously, when you're hyperventilating, you're exhaling a lot of carbon dioxide. So, first thing that's going to happen is high PO2. That's before any compensatory responses. Okay, so this is talking about immediately the direct immediate effect: high PO2 and low PCO2. What would the response be? Now you have high PCO2. What would the response be? Okay, you want to match. Do you guys remember that whole thing about the what's it called? Wait, this is it would cause both of these things. Hypocapnia. Wait, this case will be for this, and this will be for this. So, do you guys remember that whole thing about VQ? VQ, right? Ventilation perfusion. So, do you guys remember that? Ventilation perfusion. Okay. So the first thing that's going to happen is this will be increased. When this increases, ventilation increases, you will have hyperoxia and hypocapnia, both of those things. Low PCO2 levels and high O2 levels, okay? Because you're getting a lot of oxygen, and in return, you're excreting a lot of CO2. We don't want that to happen. We don't want either of those things to happen. So what are we going to do? We're going to try to bring that V back down. We're going to try to bring it back down. We're trying to reach balance with the VQ, with the ventilation perfusion ratio. We don't want ventilation to be too much or perfusion to be too little. In this case, we have ventilation to be too much. So what do? Bronchoconstriction. Hypocapnic bronchoconstriction. By doing bronchoconstriction, we decrease this back down, right? Obviously, you're constricting it right here. You're constricting the bronchioles right here. Bronchoconstriction would bring the ventilation back down, and then at the same time would bring back O2 and PCO2 to normal levels. This is as a compensatory method. Okay, so you guys don't want to make the mistake of saying that something is caused by this without considering the compensatory method. Okay, a lot of the times, and specifically and also in like very, very much exclusively in CVP, what they will do is that they'll say, for example, let's take cardio, for example. Like, what would happen when a person stands up from a supine position, right? If they stand up from a supine position, their central venous pressure obviously would decrease, would drop. Okay, but then you wouldn't be considering the compensatory methods. And because this is happening, then you would have other compensating methods to increase central venous pressure, like for example, vasoconstriction and all those things. So here we're talking about in response to this low this hyperventilation, we would get hypocapnic bronchoconstriction. Does that make sense to everybody?
So let's say the question said low ventilation. What would low ventilation cause, basically? So based on this concept here, low ventilation would end up with hypercapnia and hypoxia. Okay, that's just a straightforward like recall question. I think again, this question was worded wrong, but it's good to understand this concept. We tried to put this question even though it's wrong. We wanted to like really reiterate the idea that we need to go over this concept, make sure it's clear in our heads.
Okay. So make sure you're always thinking about the compensatory methods too. And because this is happening, what's the next thing? What will happen as a result? And what will happen in compensation? And usually they're going to be asking about the compensation part, unless they say with no compensation. And then you'll know that they're talking about the direct effect. Okay. This one's mine, right?
Mm-hmm.
Okay. So, a 26-year-old woman presents to the urgent care facility with rapid and shallow breathing for 1 hour. She describes having an anxiety attack and cannot catch her breath and complains of dizziness and tingling in her hands and feet. Her heart rate and blood pressure is slightly elevated, and body temperature is normal. Okay, body temperature is normal. Important. Which of the following changes is expected in the patients? This one is sort of a two-step thing. So you have to think, and okay, so like these are the symptoms. We're getting this, and in result, this will happen. This is, you have to think 2 steps ahead. Okay. Do we have any other answers?
Is it A?
It is A. It is A. Okay. So let's talk about why exactly it's A. It is A. Now, what's happening when you're having an anxiety attack? So the main thing that's going to happen, like not the main thing, but like one of the things that's going to happen, and specifically they described it here. They said rapid and shallow breathing. What is that? Hyperventilation, right? What's hyperventilation going to do? Immediately, first thing, we talked about this like 30 minutes ago. Ventilation, hyperventilation. 30 seconds ago. We keep talking about it. Hyperventilation will cause what? First thing you should look at. Is it increased? It's increased PO2 and decreased PCO2. Perfect. Yes. Decreased PCO2, that's the thing that's going to cause this. It is A because of the decreased PCO2. Do you guys remember the whole thing about how acidity would cause a right shift and alkalosis would cause a left shift?
Could that move right?
What? What was it?
Is that the mnemonic? Could that move right? You never heard of it?
I don't think I've ever memorized that. So ventilation would cause what? Low PCO2. Obviously, ventilation would be anxiety attack. And by the way, like you don't have to use anxiety attack because they literally described hyperventilation. But just that you can catch these keywords. So anxiety attack probably most of the time is going to be hyperventilation. So hyperventilation, low PCO2, and when you're decreasing PCO2, what's another factor that PCO2 that is dependent on PCO2? pH, right? Because you remember, alkalosis, exactly, perfectly. pH. So PCO2 decreases, pH increases, right? Because H would decrease, so pH increases, and you would have respiratory, as you said, respiratory alkalosis. Okay, respiratory alkalosis would cause a left shift. It will increase the affinity of oxygen to hemoglobin. Alkalosis, another way to say it, is low hydrogen levels. The woman is hyperventilating, and she is experiencing respiratory alkalosis. As we know, high H plus shifts the curve to the right, like this, or actually not like this, because this is not reaching the same levels. Like this, I guess. And low H plus shifts the curve to the left. Okay, so it's alkalosis.
So they did go over the affinity, this graph, right?
Yeah.
This is to mention the mnemonic that. Okay. Is this in a different lecture? The one after?
It's the same one. The graph that you're talking about. It is that one.
Okay, so could that move right? If I remember correctly. Correct me if I'm wrong.
I don't know what this mnemonic.
I know, but correct me if I'm wrong. Sure. What I'm saying. So CO2. CO2, acidity, or high H plus, obviously. D3, which is vitamin D. Exercise and temperature.
Yes.
So when we have an increase in any of these, then it would move right. So the graph would move right. Okay. That's correct,
Yeah,
right?
yeah.
So
I don't think they took vitamin D3 though. So yeah, but just remember the rest.
Yeah. But yeah, so basically we're talking about CO2. Acidity is obviously also pH, but here you need to understand that it's not increasing pH, it's acidity. So that's decreasing pH. And then exercise is increase. Exercise is could be anything. That could be increased temperature. It could be anything. And then increased temperature that would move the graph to the right. Okay.
Yeah. So if they say so, there's keywords that they're going to give you. So person's having an anxiety attack, hyperventilation. Person is having a fever, right? Also would cause a right shift because increased temperature, fever, right? All those things. Okay. Question 2 for blood gas transport. An increase in which of the following would increase the O2 affinity of hemoglobin? Any idea? Okay. E. Yes.
Yeah,
Perfect.
This question you could also
Yeah, it's the same thing.
Connect to
Right. Yeah.
this
So
is the D.
yeah.
Is the, yeah.
Right. Yeah. Basically, cadet. But yeah. I don't know about you guys, but I'm not. I'm a big fan of. I'm starting to become more of a mnemonic guy. But in first year, I sort of just relied on understanding things and like using my own little silly methods of understanding things. So the way that I like to think of it is I like to remember that carbon monoxide is just like the worst person on earth. It's just a very evil person. Because not only will carbon monoxide steal all of the hemoglobin away from oxygen, it will also hold off of oxygen from leaving and getting into the tissue. So that's the way that I like to think of it. Because when you're increasing affinity for oxygen, you're not allowing the oxygen to be unloaded into the tissue. Okay, so you would be causing hypoxia, and this is just based off this increased affinity. When you're increasing the affinity of oxygen to hemoglobin, you're making sure that the oxygen is not leaving to any of the tissues that it needs to go to in order to provide, oxidative phosphorylation, all those things, right? You're not allowing that to happen, and that's why carbon monoxide is just a very, very evil person because it's doing two horrible things. It's taking away any carbon monoxide. It's taking away hemoglobin from oxygen. It's also increasing the affinity. Of sorry, 1 second, guys. Yeah. Sorry about that, guys. Yeah. So it's going to be doing two things. It's going to be taking away the hemoglobin from oxygen. It's going to result in less free spaces for oxygen, the hemoglobin, and it's going to be increasing the affinity of oxygen at the same time, which will impair unloading of oxygen into the tissues. Does that make sense to everybody? Any questions? Does anyone have any questions? Okay, let's move on. Right, okay. A 62-year-old man at sea level breathes the gas mixture containing 21% oxygen. That's normal. He has the following arterial. Wait, you guys are answering this already? He has the following arterial blood gas values. PaO2, arterial PaO2, 60 millimeters mercury, and PaCO2 is also as close to 70 millimeters mercury. Which of the following is the cause of the hypoxemia? Few different answers.
It's an interesting question.
Okay. Can somebody tell me why you think it is D? Why do you think it's D? For this one, you have to do a little bit of math. So before you guys try to work out some of the finer details of this one, like the actual formula stuff, and then you can try to answer it. Okay. Don't we look at CO2 immediately without having to solve? Listen, yes, but it is important to be able to solve this. You are right, by the way. The answer, guys, by the way, the answer is A. The answer is A. It is. But for this question specifically, there's a deeper way of solving it that will help you a lot with solving other questions. Okay, and it will, like, there's a table in this lecture that's super insanely, extremely, like, I can't even stress enough how important this table is to study, and solving this question in the formula method will help you a lot in understanding that table.
You have the table, right?
I do have the table. Yeah. So let's get into it. So the answer is A, hypoventilation, and you can tell immediately by the CO2. But let's do this a different way. Let's do the formula method. Let's actually sit here and calculate all of the things that we need to calculate in order to determine what's causing this hypoxemia. First of all, let's do inspired oxygen. We can assume that everything they gave us, all the values they gave us are normal, because they said specifically sea level, right? It's 21% oxygen. Sea level means like it's 760. And we're assuming that, that everything's normal. They didn't say anything different. So inspired oxygen, obviously it's, as it says here, PiO2 equals the fraction, which is 0.21, because they said 0.21. By the way, guys, when they give you values like 21%, that means they want you to solve. If they were to give you just PaCO2 and say, what is this? And you would say hypoventilation, you'd be right. But since they gave you the values, it means they want you to solve, because there's a deeper thing that they want you to understand. Okay? You don't always have to solve, or you don't always have to use the formulas. But for me, it's always, better safe than sorry. So if they give you values, try to see what they're trying to tell you. So 21.21 times PB, which is 760, minus 47, because 47 is always the pressure of hydrogen in the air. And that will give you 150 millimeters of mercury. Okay, then you get the alveolar oxygen. And one of you guys said the formula a while back, but it is PiO2 minus PA alveolar or arterial, because remember, the difference between those two is very, very little.
Yeah.
So it's it's negligible, and we consider it the same. PaCO2 over R. And R is 0.8, so you do the math and you input the values and you get 62.5. This is PaO2. PaO2. That's telling you, oh wow, my alveolar oxygen is low. Okay. Now, some of you said right to left shunt. Right to left shunt would be true if the alveolar oxygen was normal, was 100 millimeters mercury, because then you would have something wrong with the actual perfusion, of it, and that's what would be decreasing your arterial PO2. But the main thing here is that there's no gradient, right? There's no gradient. So because this 62.5 is very close to the 60 that we find here, very close, you consider it to be normal perfusion. That means the gradient is normal. So alveolar minus arterial pressures are normal, which means alveolar pressure is already low to begin with due to the increased PaCO2 levels. The only two things that can give you normal, that can give you a normal AA difference, so an unchanged difference, are what's called hypoventilation and low and high altitude. The only two things. Okay, this is going back to this table, by the way. We're going back to this table. So the two things that you're looking at is increased CO2, and the normal gradient. The normal gradient means that it can only be either high altitude or hypoventilation. How do we know that it's not you at high altitude? Well, first of all, they said it. They said he's at sea level. Okay, but second of all, you can look at the inspired oxygen. If the inspired oxygen is also normal, and it is here 150, that means it's not you're not at a high altitude, you're at sea level, and you still have this normal gradient while at the same time having hypoxia. And this is telling you that it's hypoventilation. Okay. Now, again, you could, as one of you mentioned, yes, the CO2 is a major indicator for hypoventilation, right? It's a major indicator for hypoventilation. But the fact that they gave you the values means they want you to solve for it, and it's very important to sometimes solve for these things because you want to apply that knowledge onto this table. Okay. So using this table, what we see here is obviously these are all decreased arterial oxygen, but what we also have is increased O2, right? Increased O2 right here. So it could only be hypoventilation. Okay. If it was normal PaCO2, then it would be one of these three things, and then it might be right to left shunt. Okay. The fusion problems also you would have a normal PaCO2. The fact that you have an increased PaCO2 while at the same time having unchanged difference, that's telling you it's hypoventilation. Does that make sense?
I think we just kind of bombarded them with a lot of stuff.
Yeah, we've been going at this for a while, guys. It's fine if you're getting a little bit
up something.
tired.
It's not really as important to know here, but so if they did ask us to get the alveolar oxygen, but they didn't give us the R, what would we do? If they told us to get the alveolar, like the PaO2, the alveolar oxygen, but then they didn't give us the R. Can we still solve for this equation here?
Yes.
Yes, we can, because PaCO2, because the PaCO2 over PaO2 is most likely going to be 1. Usually is going to be 1. So it's good to stress on the point if they don't give us R, we can still solve for that equation if we just subtract PaCO2 from PaO2. The doctor also mentioned that it most likely will not come. Like they will probably bring an R, like a fraction for R, like a.
They will probably.
A value. No, they will.
Yeah, they will.
I'm just saying, just in case if they don't, like you guys will know that like PaCO2 is sometimes equal to, sometimes equals to 1, so you can use the 1 there. Okay. Okay. And then VQ mismatch.
Okay. VQ mismatch. I think this is the one that needed the most help based off of the form that we sent. So you guys seem to have a bit of trouble with VQ mismatch. That's why I tried to add. You know what? I'm just gonna. It's a bit of a spoiler, but first question: regional differences in ventilation. Regional differences meaning differences like within the same lung, and perfusion of the normal upright lung affect gas tensions in the pulmonary blood. Which of the following best describes the gas tensions PO2 and PCO2 in the alveolar capillaries at the apex, at the top, or the base of the lung in a healthy individual standing upright? So basically they're saying, what do you see in the apex, or do you see in the base? That's what they're saying. Okay. Okay. A few different answers. Okay. Okay. No worries. So the answer, so I'm getting D's and A's mostly. The answer is actually B. So, but no worries. It's a little bit of a difficult concept. But first of all, I want to hear from you guys. Why do you think, let's say A? Why do you think it's A?
Because at the apex there is low compliance, so low ventilation.
Low what?
Low ventilation.
Increasing compliance at the apex because like the spring, if you take the example of the spring, so the tension at the apex is higher, so less compliance. That's why
Less
there's
compliance.
less going on.
Okay. Well, so we don't really look at compliance at all when we're talking about the gas tensions in the pulmonary blood, because we're talking about the gas tensions. We're not talking about the inflation and deflation of the lungs. We're talking about the entire ventilation perfusion thing. So this goes down to the VQ ratio. Okay, so
like higher at the bottom, at the base. That's why there's higher PO2, right?
You're talking about the ratio? The ratio is higher at the base?
No, I'm saying that the ventilation is high. It's higher at the base, yes.
Okay.
And it's lower at the apex.
Okay. Both, okay, it's a very, very good, it's a really, really good concept to clear up. We don't care about just the ventilation, and we don't care about just the perfusion, okay? Because just ventilation alone will not cause these changes. What we care about is the ratio, ventilation to perfusion. That's why the entire lecture is about just the ratio of VQ. And when you have a VQ mismatch, how will that affect your pressures? So never, like when it comes to this lecture, you shouldn't really say, okay, my ventilation is higher here. My ventilation is higher here, so I'm going to have higher PO2. You should never think that way, because then that's when you start to get confused. Because you are right. You do have, if you go down to this, you do have more ventilation here at the base than you do at the apex. So if we're looking at just the ventilation, yes, the answer would be A. You should have the highest PO2 at the base, but we're not looking at just the ventilation. We're looking at the ventilation and the perfusion together. Okay, so we're looking at the ratio. The ratio, although the ventilation is higher at the base and perfusion is higher at the base, the ratio is highest at the apex, because if you look how small the perfusion is when compared to the ventilation. The ratio, so let's say, for example, ventilation up here, it's 1, and perfusion is 0.00006. Okay, 1.0.00006. That's your ratio at the top. Like, I'm just giving examples. And at the bottom here, it's 10, and this is 5, right? 10 over 5. 2, and this is what, like, it's a bunch of, it's really, really high. So the ventilation, yes, is higher at the base, but the ratio, so this would give you 2, and this would give you a big, big number. The ratio is higher at the apex. Okay? The amount of oxygen, not partial pressure, is greater at the base than the apex because of perfusion, right? Well, the perfusion is higher too. But again, if you have higher ventilation than perfusion, a lot more ventilation than perfusion,
You have a higher ratio.
you have a higher ratio. And when you have a higher ratio, the capillaries will be more loaded with the oxygen. Okay? Because there's less blood. So the blood that's coming in will be taking up all of the oxygen because there's so little blood. Okay, like imagine, okay, let's say for example you have you're a baker. Okay, you're a baker, and you have a bunch of what's something that you bakeries? No, muffins. Muffins. You have a bunch of muffins to give out to everybody. You know what? Scratch that. You have two bakeries. Okay, both of them sell muffins, the same exact amount of muffins too. So we're just going to consider the same amount of muffins. One of them has 300 people lined up to take all of the muffins, and the other one has 3 lined up to take all the muffins. Which person individually will take the more muffins? The one at the first bakery or the one at the second bakery?
Second.
The one at the second bakery, because there's less people. So the individual person will be taking more muffins than the person in the first bakery, right? Mm-hmm. So that's what's happening here. You have less perfusion in the apex, meaning the blood that is reaching that alveoli will be taking more of that oxygen than the ones that are coming in the base, because there's less perfusion and a lot more ventilation. Even though the ventilation is more at the base, the ratio is higher at the apex. Does that make sense?
I have a question.
Yes.
When do I know when they're asking for the ratio and when they're going to be asking about just ventilation or just perfusion?
They wouldn't ever ask about just perfusion. They would only ask about ventilation alone in the context of like hypo or hyperventilation and the amounts of PCO2. That's why we say that PCO2 is so important in ventilation, because that's the first thing that's going to change. Meanwhile, and PO2 is very, very open to many factors and many effects and all the VQ mismatches and the whole thing. Okay, so when they give you PO2s, and like it's specifically like we're talking about anatomically apex or base. Like if they say apex or base, it's VQ. If they're talking about like something else, then it might be hypo or hyperventilation. But if they ever give you apex or base, it's a VQ. You should be looking at the ratio and not the individual thing. Okay?
Okay, thank you.
Do we always look at the ratio itself? In the context of this lecture, when they give you like for example, like by the way, guys, this is when we talk about VQ mismatch, the difference between this lecture and the rest of the lectures is that we say, for example, hypoxia in another lecture, we're talking about overall blood. Overall, the oxygen is low in all of the blood, everywhere in the body. In VQ mismatching, we're talking about specific tiny capillaries coming out of a specific region of the lung. That's the main thing. It's a specific region of the lung. They're not going to tell you you have low PO2 overall, and you're going to be talking about the apex of the lung. No, you're going to be talking about the capillary leaving the apex of the lung. You guys get it? So in this lecture, we're really, really zooming in and looking at the different parts of the lung and how the blood and how the gas tensions will change in each region of the lung. Meanwhile, in other lectures, when we're talking about overall hypoventilation, you're talking about everything, the entire lung and the entire body, and all of the like your overall gas tensions in your blood. So if they say apex or base, it's the ratio, the VQ. Does that make sense?
Yes.
Okay, perfect. Now, this lecture is, this question is very, very similar to the first one, but I wanted to make this distinction. The apex of the upright human lung compared with the base has perfect. Wonderful. Can somebody tell me why it's not B? I was kind of hoping that some of you would say B just so that I could clear that up. But yeah, why is it not B? Doesn't the fact that we have a higher PO2 in the apex also mean that we have the highest ventilation? Why isn't it B compared to the base? Yeah, pretty much, yes. So again, I'm going to use the same diagram. You notice here that we actually don't have higher ventilation in the apex when compared to the base. We have higher in the base, but the ratio is higher. Okay, so this is wrong because it's actually higher ventilation in the base, but the ratio is higher. So the ratio at the apex has highest V over Q ratio. So that will give you highest PO2. I kind of expected you guys to put B, so I put very common mistake. Okay, no, those you guys didn't make a mistake. But yeah, the highest VQ ratio is in the apex, not the highest ventilation. Does that make sense? I think it makes sense because it's very similar to the first one. Okay, I put 3 questions in for this lecture. Wait, so the question is asking about the ratio. Again, what I mentioned to you when we're talking about apexes and base, always think ratio. So this is apex and base
to the base.
We're talking about comparing specific parts of the lung to one another. So apex to the base will have a higher PO2. Like the capillaries leaving the apex will have higher PO2 than the capillaries leaving the base. Again, in this lecture, we're really zooming in on the lung. Okay, in other lectures, you wouldn't see us talking about how the base has higher perfusion than the apex, for example. You wouldn't see us talking about that because we're talking about overall systemic changes, like hypercapnia all over, hypoxia all over, right? Here we're talking about more PO2 just from the apex, not all over. This volume of O2 down is more. Yes, but again, it's about the ratio. Like you really, I cannot stress enough that it's the ratio we care about in the context of this question. The volume, it is down. The volume at the base is greater than the volume in the lungs, but like think of it as like a give and take. You're giving ventilation, like like from ventilation you're giving air, and the perfusion is taking that oxygen. You know what I mean? So it's a give and take. So if you have more giving than taking, right? Like, you know what I mean? You have more ventilation than perfusion, you're gonna have a higher PO2. Okay, it's a bit of a difficult concept to nail down, because whenever you think you have it down, you'll get another question to mess you up a little bit. So if you understand it, like great, wonderful. If you don't understand it, at the very least, just remember the apex of the lung will have a higher PO2 than the base of the lung because of the ratio. At the very least, just remember the ratio. The ratio is higher at the apex than it is in the base, and then from there build build up and be able to solve questions more. So since the ratio is higher in the apex, you're going to have a higher PO2. But if you understand it fully, and you understand that it's because of the very, very low perfusion in the apex, and that's why we get the high ratio. If you understand that, then perfect. Go and help more people understand it. But if you don't understand it, at the very least, be able to remember that the apex has the highest ratio, VQ, the highest VQ ratio, and at the base you have the lowest VQ ratio. And then you'll be able to solve all the questions from this lecture with no problem. Because all the like this is what the questions are going to be like in your final when it comes to this lecture. So as long as you remember this concept, not understand it, as long as you remember it, you should be fine. Okay. Perfect. So I think we have
one more lecture.
We have one more question for VQ. So this is we put in a few more questions for this lecture just because we thought that it would need the attention. Which of the following causes of hypoxia is characterized by a decreased arterial PO2 and an increased gradient? So before we okay, or we could just answer it. Yeah, also works. But before we answer, obviously you guys already answered this. Since we have this down and this up, what does that tell me about my alveolar PO2, PaO2, my alveolar PO2? If this is up and this is down, alveolar.
Decrease?
No, increased, right? Because this is down and this is up. Because your gradient is high, this is up, and this is down, right? Which will mean this is up, right? Your alveolar. So since your alveolar pressure, your alveolar PO2 is increased, that immediately will cancel out. Hold on. Immediately will cancel out A and E. Immediately.
Because these are normal AA, right?
Because they're normal AA gradients and normal and low alveolar pressures. Low alveolar pressures and normal gradients. Okay. So it's not A, it's not E. D, you wouldn't even have decreased or sorry, like D is not even one of these factors that we look. Anemia we don't look at all, because anemia we didn't really take that in specific. And the increased gradient you wouldn't find with carbon monoxide poisoning. Okay, so that's why it's B. So did I add 3 of slides that look the same? I think I might have. Oh, there it is. Okay, again, this is what we're going to look at again, because this is super important. So who can tell me which one of these we're looking at in here? Obviously, it's increased gradient isn't in the hypo.
Yeah,
either.
Yeah, it's normal.
Yeah, increase. Yeah, see the gradient. This is the gradient, by the way, guys. This is the gradient. AAD means difference in big A and small a, alveolar arterial. So unchanged in hypoventilation and in high altitude. It's only ever increased in diffusion problems, increasing in right to left shunt, which is the case here, and increases in VQ, like more VQ mismatches, basically. Okay. So as for this little whole thing, there's really like it's kind of hard to Like this one I'd recommend just remember it. Just try to memorize that. For example, this one, 100% oxygen would work. This one, it wouldn't work. But most of the time, for example, they wouldn't bring a question, like they shouldn't, or they probably won't bring a question with both of these answers in them. Like probably the questions that you get on your final are going to be like this simple, where you'll be like, okay, so it's not A, and it's not E, and we didn't take C, we didn't take D. You know? So you shouldn't have any worries with that. Okay. I think this is our last.
This is our last lecture.
This is the last lecture.
This is a kind of an annoying lecture because it's basically all memorization. There's not really a lot to understand here. But let's go over the questions. The wife of a recently married 24-year-old medical student reports that even though her husband doesn't snore, he stops breathing for periods of 1 to 2 minutes while he's sleeping. His physician refers him to a study and pulmonary function testing included ventilatory response curves. The test confirmed the apneic episodes during sleep and showed depressed ventilatory responsiveness of both peripheral and central chemoreceptors. So peripheral and central chemoreceptors both contribute to the increased ventilation. So literally the whole question we didn't need. All we needed to know is they're talking about peripheral and central chemoreceptors contribute to the increased ventilation that occurs as a result of what? So basically, what makes peripheral and central chemoreceptors increase ventilation? That is the question.
This is where you start to think about the compensatory methods.
Yeah, so when do we have an increase in ventilation? When do we have hyperventilation, basically? So yeah, again, as you guys said, yeah, so it is C. So an increase in carbon dioxide tension would make peripheral and central chemoreceptors increase ventilation. So those would happen in the corroded aortic bodies, I think. And then they basically have in the lecture, it says that if there is ever an increase in PaCO2, that would result in the peripheral and central chemoreceptors to increase the ventilation. So A, why is A decrease in arterial oxygen content? So again, because they didn't here they talked about peripheral and central. When we talk about oxygen, I think they have in the lecture that when there's peripheral chemoreceptors when peripheral chemoreceptors increase ventilation due to the decrease in the pH and PaO2. So here this would be correct, yeah, if we were talking about peripheral chemoreceptors only. If only peripheral chemoreceptors were to increase ventilation, then we're talking about a decrease in arterial oxygen.
Yeah. Plus, guys, you also want to remember that your main trigger, main stimulus for your increased ventilation is always your CO2 levels. Like the CO2 levels are such a major factor in determining the rate of ventilation that immediately if they say what increases ventilation, your first line of thought should always be carbon dioxide, and if not carbon dioxide, like either carbon dioxide or not carbon dioxide. You know what I mean? But you should always think of those things first. So they said peripheral and central chemoreceptors, right? Your peripheral, so your peripheral chemoreceptors are like directly affected by your by your oxygen
and pH.
Okay, but not central. Central is mostly pH. Central is mostly pH. And what's going to contribute most of the pH? The decrease in carbon dioxide tension, which means
pressure as well too.
Decreased HADA, which means increased pH, right? Does that make sense?
So again,
increase, so decreased pH. So it wouldn't be E because it's an increase and it's actually a decrease in pH. It's not an increase. Do you guys understand? So since it's both peripheral and central, peripheral will tell you oxygen, central will tell you pH, and you can't get like a pH you can't determine a pH from oxygen. What you determine it from is the CO2. So it's the CO2, and CO2 is a major player in the in determining the rate of ventilation.
Again, this stuff is all there's not really a lot of understanding. It's all like memorization. So like you guys are just like if you guys are having trouble with this lecture, you guys have to like go over it again, just to kind of memorize what different chemoreceptors are. Yeah, go down to question 2. Okay. So a 42-year-old woman with severe pulmonary fibrosis is evaluated by her physician and has the following arterial blood gases: pH is 748, PaO2 is 55, PaCO2 is 32. Which statement best explains the observed value of PaCO2? Again, also a pretty like a recall question again. We mentioned in the first question too. So basically, all we need to know is which values change because of the PaCO2. So first, PaCO2, is that decreased or increased? So it's 32.
Decrease.
Decrease. So what will cause a decrease in PCO2?
Increased pH.
No. Like what will cause directly the decrease in CO2? Not specifically from this lecture. I'm talking about for all of pulmo.
Like
ventilation.
How does it affect ventilation? That's what you mean, right?
No, what will cause it? What will cause the increased PCO2 or the decreased PCO2? Increased ventilation. Then so right now you're working backwards. You have the final results, and they're telling you what causes the final results. So you have the step before it, which is increased ventilation.
Yeah.
Right. The step before, they said what causes CO2. You start to think backwards. Okay, what usually causes decreased PCO2? Okay, increased ventilation. So now, what would cause the increased ventilation?
I think,
and that's where you start.
One of you guys said increased pH, which is correct. Yes, there is an increase in pH. And then now with this kind of information, and then I guess assuming you guys know peripheral and central chemoreceptors, what they do, which of the following what the following happens here? Okay, so what is going on with PaO2? Is PaO2 increased or decreased?
Decreased.
Decreased. Okay. Decreased PaO2. Okay. So now let's go over it again. Okay. So first of all, we said let's look at the carbon dioxide. Here, carbon dioxide, we have a decrease in carbon dioxide. First thing we were taught that when there's a decrease in carbon dioxide, we are mostly looking at hyperventilation. Okay.
Or at least increased ventilation.
Increased ventilation, yeah. So there's low PCO2, and then we look at the oxygen. We're like, okay, oxygen is also low. So what do you think our body here? What's the most important thing for us to do right now? If we don't have a lot of oxygen, we have low oxygen and we have low carbon dioxide. We're going to be hyperventilating or increasing ventilation.
But due to the low oxygen levels, that's the main thing, right, guys? Because we have the low oxygen levels, we're going to be telling our body, wait, I need more oxygen, I don't have enough, and I'm going to be increasing the ventilation rate. That's what's going to cause that drop in carbon dioxide. So immediately that tells us it's not A nor B.
Because pH is not fully.
Because we're talking about PO2 and not pH, because that's the main thing. The fact that they gave you a low PO2 means they want you to look at this as the cause. So this is the cause. Does it inhibit breathing? Yeah. So it is D. It is D. It doesn't inhibit breathing. It actually stimulates breathing. But does it stimulate breathing in peripheral chemoreceptors or central chemoreceptors? Yeah, it's peripheral. So that's why.
Okay. I think it's important to understand again why we're not looking at the increased pH in this question.
Yeah, so we're not looking at the increased pH. First of all, increased pH will be central, so it's not A. Okay, but the second thing, something is causing PCO2. Okay, now PCO2, something is causing the decreased levels in PCO2. Now, okay, if you have a decreased levels of PCO2, you're getting alkalosis. right? You're having alkalosis. So it would be increased pH. They're asking you what is causing this. Okay, the PCO2 would then go and cause this, but it wouldn't be caused by this. You understand? So the first thing that happens is the CO2 would change, and then the pH would change. But what would cause the CO2 to change? It wouldn't be the pH. Do you understand? Because the pH is increased by the CO2, so it cannot happen before that. You're looking at what's happening before that to decrease this, to decrease the CO2. Does that make sense, guys? And you're looking at it. Okay. Okay, no worries.
I think also we mentioned we failed to mention that increased pH never stimulates breathing.
Yeah.
It inhibits breathing.
Yeah, that's another thing.
But you can go over again.
So okay, we want to think of the this question basically gave you a bunch of information and then asked you to go backwards from it. They said, okay, so the end result is this. What caused it? They said, here's a bunch of information. Here's the end result. What happened in the middle? So they gave you PO2. PO2 is 55 millimeters mercury. It's low. We can tell that it's low. And they gave you PaCO2, which is 32 millimeters mercury, which is also low. Okay. They said, what causes this? Not what causes this. What causes this? Which statement best explains the observed value of PaCO2? Okay. Now, if you have decreased PCO2, you would have decreased levels of H+ ions, and then you would have an increased pH. That is true, you would. But they're not asking you what is this causing. They're not asking you what would be the results. What would be the result of decreased levels of PCO2? That's not what they're asking. They're saying what is causing it. What is the thing that's happening before this step that is causing the decreased levels of PCO2? It cannot be this. It can't be increased pH, because increased pH would happen after the CO2 has gone down. Do you guys get it? They're asking what's causing this, not what's caused by this.
The woman has fibrosis, so that I think that's a pretty good like hint at what, like, that they're trying to ask you about what is going on with O2 to cause what's going on with CO2.
Yes. So the main thing that they're asking about is this. They're asking obviously about what is causing this, but the thing that you should be looking at is not the pH, because the pH comes after. You're looking at the PO2 because that's what they gave you. That's what they told you already is low. So when you have low PO2, what's your body gonna do immediately? Regardless, like, they don't care about your body. If you have low PO2, your body doesn't care about a single thing. Its main focus is to bring in more oxygen into your body, regardless of what it does to the CO2 levels. That's why the decreased PO2 will stimulate more breathing. So if we start now, now we work backwards. Now let's work forwards. So decreased PaO2, okay, increased breathing via peripheral receptors, okay, and then decreased PaCO2. So they gave you this, and they asked you, what's this? What's this? They're asking you to work backwards. So first this, and then increased breathing, and then this. But you wouldn't be able to say, for example, that the increased pH will stimulate breathing, and then I'm also going to have decreased PaCO2, because those, like, that will make it worse. Like, the decreased PaCO2 will make it will only worsen the alkalosis. It wouldn't make it better. Do you guys understand? So it's all about cause and effects. This is happening.
Even if we were to look at this question, let's say we didn't like try to think about it the way we thought about it right now, and we tried to, like, just like go over and just like take questions, or like remove questions that we thought, or answers that are wrong. Okay, if we were to do that, first of all, okay, we have something is going on with PaCO2. Okay, first of all, increased pH. In the lecture, it says it does not stimulate breathing. It inhibits breathing. Okay, so right away, those two are wrong. They're out. Okay, and decreased PO2, all of them are decreased PO2. Does decreased PO2 stimulate or inhibit breathing? Not from this lecture only. We know this from different lectures. When we have low oxygen, when someone is not breathing well, what are we trying to do?
Stimulate
breathing.
Exactly.
So right away, boom, this is gone. Okay, and then it comes down to, okay, does decreased PO2 stimulate breathing by peripheral or central?
And this
here-
is recall.
This is recall. We know it's peripheral, so the question is D.
The answer,
Okay.
yeah.
The answer is D. Like so it's good to like, yeah, it's good to like, even if like the question is, it sounds wrong, like sounds tough, and like they're trying to like get you guys to like think about it in ways that you can't think about it. It's good to like just go on the like go over the answers, just like take like cross stuff that you know is wrong. Okay, last question is also pure recall. Hypoxemia produces hyperventilation by the direct effect on what? This is also like there's not really a lot of understanding here, just pure memorization. Hypoxemia. Okay, hypoxemia, perfect. Yeah, so it is E. What do J receptors do? What do those guys do? There's no. Forget what they do. They did something with the.
They're I think they're having to do with like the cough reflex,
Yeah.
if I'm not mistaken.
But these
Something
are
about
not
extension.
chemo. These are.
But these are not chemoreceptors.
Not
That's the main thing.
chemoreceptors,
These are
yeah.
stretch receptors.
Okay, and then yeah, and then phrenic nerve. You guys know what phrenic nerves does, is innervates the diaphragm, and then these two, like, I think we didn't take them in chemoreceptors. We took the only ones that we took for hypoxemia were carotid and aortic body chemoreceptors. That's but you guys are answering correctly. Do you guys have any questions about it?
Okay. Do you guys have any questions about any single thing in pulmophysio? Anything we've talked about today that you're not fully understanding that we can go over? How many people are left? Okay, perfect. I'm gonna take your word for it.
Yeah, thank you guys for sticking with us for the past
2.5 hours. Wow. Okay.
Hopefully you guys,
hopefully you guys, inshallah, you all do well. Inshallah. And please fill out this form. Help out our wonderful subheads, the academics team.
Yeah, we need to.
Of course,
it's only one question they said, so it'll take you half a second.
It won't take you that long. Give us good feedback
or bad feedback.
Whatever you
feedback
want.
helps too.
Yeah.
But we if you guys have any questions about the exam or anything, like, you guys will have our information in the beginning. So if you guys have any questions about anything, please let us know. Other than that, I wish you all the best for your exam.
Thank you guys so much. Here's our information if you guys need it. And I'm gonna keep this on the feedback form just in case any of you wanna still take it.
We will send you this PowerPoint.
Yeah.
It's just condensed with like the slides.
Yeah. It's a lot of slides.
It's a lot of slides. We'll send it to you guys, inshallah, like within the next hour or two.
Yeah.
And yeah.
Okay. Thank you guys so much. Have a good night. I guess what time is it? 6 almost.
Yeah.
Yeah. Perfect.
Thank you guys.
Okay. And thank you, Mariam, for sticking with